Hello everyone. Today this is a video on vectors and projectiles. So the first thing we're going to do today is discuss some properties of vectors, how to add them together, how to subtract them, and all of that good stuff, just so that we can have a little reminder. So if I have two vectors, let's say I have vector A and then I also have vector B, I can say that A and B are the same, right, if their magnitudes and their directions are the same. So if A is parallel to B, then I know that their directions are equal, and then I'll either know the magnitude from the problem or I'll be able to visually see it on a graph. So if I want to do A plus B, so let's say now I have A and this is my B. A plus B, when I add vectors together, remember that we always add them head to tail. You can move vectors parallel to their original starting spot as long as they are parallel. So I'm going to slide these vectors together so that they sit parallel to their original position and they are head to tail. So when I add them together, the answer to that we call our resultant, and it's a vector that runs from the tail of A to the head of B. Sorry guys, I'm having some ink issues. Okay. So we would call this vector the resultant. And in this case, let's just label it C. If I want to subtract vectors, well, that's like adding the negative. So I could draw, instead of A plus B, if I wanted to do A minus B. Here's my A vector again. So if I wanted to add the negative of the B vector, I would essentially just flip the direction of my B vector. And then my resultant becomes this distance here. This is my C. So these are just some basic review properties of vectors. Now we're going to get into something new when we talk about vectors, and that is our something called IJK notation. IJK notation. So if we have a position vector that's given by a point, so let's say here is our xy axis, and let's say I have a point here, and let's say the coordinates for this particular position is 3, 4. Then the position vector that describes this particular location, we usually denote it with an R, would be 3I plus 4J. So the I component corresponds to what's happening in the X direction. The J component corresponds to what's happening in the Y direction. And then if I had a K component, that would represent what's happening in my Z direction. Now I know last year we only dealt with motion in 2 dimensions, but sometimes we do have to think about the third, or that Z axis, depending on the problem. So let's do an example with IJK vectors, just to get an idea of how they work. So let's say we have an object whose initial position, we'll say, is right here. And we'll say its initial position, or its initial xy coordinates, is, let's say that that's 5, and let's say that that's 10. And then let's say sometime later, let's say at t equals 20 seconds, this object has moved from this position, let's say, to this position. So this is 5, 10. And let's say this is 9, 6. So this is a difference of 20 seconds. So let's talk about its velocity, right? Its average velocity as it moves from this dot to this dot. So the first thing we need to do is to determine what is its velocity in the x direction, what is its velocity in the y direction. So let's look at what's happening in the x direction first. In the x direction, we're starting from 5 and we're going to go to 9. So the distance, or the displacement of the object, which would be 9 minus 5, over the time, which would be 20 seconds. So in this case, it would be 0.2 meters per second. So let's look and see what's going on in the y direction. We have from 6 to 10. And again, that took 20 seconds. And then that would be negative 0.2 meters per second. So if we were to write its velocity as an ijk vector, we could say that its velocity vector is going to be defined as 0.2 in the I direction minus 0.2 in the j direction. And then to actually find our final or our average velocity, we would need to resolve this vector, or in other words, we would need to do Pythagorean. 0.2 squared plus 0.2 squared, and then we would square root it. And that would give us our answer. So let's do that real quick. So that gives us a final actual velocity of 0.29 meters per second. All right, so this is one way that we can talk about our average velocity for an object that's traveling in a position grid. So let's do a couple of examples in a PowerPoint real quick. And let's go to here. All right, so a particle moves in the xy plane with constant acceleration. We have, at time 0, the particle is at 4 and 3, and it has a velocity of 2I and 9j. And the acceleration is given by the vector 4I and 3j. So find the velocity vector at 2 seconds. So what we're going to do here, I want to make sure I don't accidentally advance the slide so you don't see the answer just yet. So to find the velocity vector, we're going to look and see what's happening in the I direction, and we're going to apply our I acceleration to the I velocity. So after 2 seconds, right, we can use a kinematic if we need it, but we probably don't need it. The acceleration is 4. My time is 2, and then my initial velocity is 2. So that gives me an acceleration in the x direction of 10 meters per second. And then I can rinse repeat with the y information. So that's 3 times 2. Now it's going to be minus 9, since the initial velocity in the y direction is minus 9. So that's 6 minus 9 is negative 3. So the velocity vector then would be 10 meters per second I minus 9. Oh, sorry, not 9. 3 per second j. All right, so let's find the position vector at t equals 4 seconds. Give the magnitude and the direction of the position vector. Go ahead and erase this work real quick. And then we'll go and we'll do that part. Okay. So Position-wise, we can just do another kinematic. We're going to do the same thing, but we're going to do it in the x direction and the y direction again. And then we will do Pythagorean to find the magnitude and direction of the position vector. So in the x direction, right, we always use r for our position. So we have an initial velocity in the x direction of 2 times t plus 1/2. A in the x is 4 times 4 squared. And then in the y, same thing, except we use -9 times 4 plus 1/2, 3 times 4 squared. So this one will be 40, and then this one will be -12. So when we write this, we can say the r vector at 4 will be 40 meters I hat minus 12 meters j hat. And then to find our magnitude and direction of the position vector, we should do our Pythagorean. So we would do 40 squared plus 12 squared, and then we would square root it. That gets us about 42 meters. And then from there we can do inverse tangent to describe our angle. So we can do inverse tangent. If this is 40 and -12, we're looking at 40 and -12. Here on our xy plane, if this is 40 and -12, here would be our vector, 40, -12. So this would be our angle, right? So inverse tangent of opposite over adjacent, so it would be 12 over 40. And then that would give us, I hope, if my calculator's in degrees, which it is not, the correct answer, which is about 17 degrees-ish. Alright, so why do we care about IJK notation? Sometimes in some problems they will give you, instead of telling you the actual value, they'll instead give you the acceleration or velocity as a function of the graph of a position, right? So, or of a coordinate system on a graph. So it's a little bit different way to talk about vectors, but as long as you remember that I means what's going on in the x direction, j means what's going on in the y direction, k means what's going on in the z direction, you'll get the hang of it. So there is one more problem I think I want to make sure you guys see. Maybe not. Maybe not in here. Okay. Alright, so let's go here. So one more problem I want to do with you is an example from your textbook, but I want to go ahead and walk you through it. So let's say we have a position vector for an object that is given by this. And we're going to have to put a time here. Here's a t there, I ran out of space. Minus 4.9 meters per second squared j hat t squared. Okay, so we're going to try to find this object's velocity and its acceleration, or rather the velocity vector and the acceleration vector. So the x and y components of your velocity, let's deal with x first, are going to be found by taking the derivative of the x components here. So what do we have going on in the x direction in our original function? We have 1.5 meter I hat, and then we also have this 12 meters per second I hat times t. So if I take the derivative of this with respect to time, my velocity in the x direction then is just 12 ms. Because there's no t here, right? So we're going to do d dt here. And there's no t in this term, so it just becomes 0. And then the derivative of this is just the constant, which is 12. So let's look at that again for the y direction. So in the y direction, what do we have? We have 16t minus 4.9t squared. So same thing but reverse. We're going to do 16, because that's the derivative of this, minus, and that's going to be 9.8 times time. Alright, so if we put these two together to make our velocity vector, we can say in the x direction it's 12 meters per second I, and then in the j direction we have all of this term. So let's draw a parentheses here. And that's our velocity vector. So let's do that one more time, and let's do acceleration. Same deal. Acceleration in the x direction, well, if I took the derivative of this, acceleration in the x would just be 0, and then acceleration in the y would be the derivative of this expression, which is just negative 9.8t. Oh, sorry, just negative 9.8. So our acceleration vector then, to answer this question, negative 9.8 meters per second squared j. And this is usually like j hat, I hat, because it's got a little hat looking thing on it. Alright, that's all I really want to talk about vectors. Let's talk about projectiles just a little bit. To review, there are two different kinds of projectiles. We have a horizontal projectile, and then we have what's called an angled projectile. Kinematics still applies to both of these, except on both of them you have velocity happening in two directions. Here you have a horizontal velocity, and then you also have a vertical velocity. With both kinds of projectiles, your horizontal velocity is constant. There's no acceleration happening in the x direction. The y direction is when we experience acceleration, because in the y coordinate plane is where gravity acts. So I'm going to draw these little x velocity vectors, and then I'm going to go through and draw the y's. So initially, when you have an angled projectile, you have a pretty large y, there's no y velocity there. Y velocity, and then you're going to lose speed in the y direction until you get to the top, and then you will gain speed on the way back down. With a horizontal projectile, you have no initial y velocity. All you have is x, because it's starting off going horizontally, and then once it starts to fall, you start to gain speed. Acceleration for both of these the entire time is negative 10, as you guys remember. And all the same kinematics still apply, except remember that we have to be very cognizant about our velocities, which velocity that we're using. Because in the x direction, the only equation we can use is this one, right? Changing x over t. Because there's no acceleration happening in the x direction, so we cannot use a kinematic to help solve for it. But in the y direction, we have all of these, all of our familiar friends here can help us out, because in the y direction is the direction we have acceleration happening. Oh, that should not be changing x, that should be changing y. My bad. Alright, I'm going to stop that video for today, and if we need a little bit more review, I will be glad to make another one on projectiles. But on Tuesday, when you guys come to class, we will do a little bit more work with vectors and getting familiar with that IJK notation. So I hope you have a good weekend.